We're going to review relative motion of two particles using translating axes. And for this, we're going to use the equations velocity of A equal to velocity of B plus the velocity of A with respect to B. We're also going to use the velocity of B equals the velocity of A plus the velocity of B with respect to A. You can see the pattern in that A is here, then for the relative, it's A with respect to B. And for over here, we have velocity of B, and the relative velocity of B with respect to A, with the other one in between. And so now we're primarily going to use the vector form of these. So we're going to have to break down our components into vectors. And then we're also going to use the acceleration of A is going to be equal to the acceleration of B plus the acceleration of A with respect to B. Acceleration of B equals the acceleration of A plus the acceleration of B with respect to A. Now, the velocity is usually going to be pretty straightforward. Just have to break the velocities into components and make vectors out of them. Now, same is true with acceleration. The only thing we have to remember is if we're going around a curve of any kind, for the acceleration, we're going to have a tangential component, and we're going to have a normal component. And we're going to have to put these into our vectors and take those into account. You recall that the normal acceleration is always going to be the tangential the tangential velocity squared divided by the radius. And remember, this is the radius of curvature of the curve. So let's take a look at this problem. It says that two boats leave the shore at the same time and travel in the direction shown. The velocity of boat A is 18 feet per second. Velocity of boat B is 22 feet per second. Determine the velocity of boat A with respect to boat B. Now, it looks like they're going at constant velocities, so we can assume there's no acceleration. And most important part of the problem, again, to determine the velocity of boat A with respect to B. Then the second part, which isn't quite as important, how long after leaving the shore will the boats be 1,700 feet apart? So let's take a look at this problem. So we have this situation here. Boat A is leaving at a 25-degree angle with the vertical. Boat B is leaving at a 55-degree angle with the horizontal. And the velocities, velocity of A is 18 feet per second. And the velocity of B is 22 feet per second. And so now we're going to have to find the vector of this. And so let's find the vector of A. And so remember, it's always the easiest to start with the adjacent. So adjacent to 25 is the y-axis. So we'll do the adjacent first. And so that's going to be 18 cosine 25 J. And notice it's going in the positive y direction. So the J component will be positive. So then the other one, if the adjacent is cosine and that's the y, then the x must be sine. And notice it's going in the negative x direction, so we'll put a negative in front like that. And then when you put these in your calculator, you get negative 7.61 I plus 16.31 J. Now look at the velocity of B. Again, this time the adjacent is with the horizontal with the x-axis. So we'll start with that. So we have 22 cos 55. Again, the adjacent's always cosine. And then plus the other one that has to be sine 22 sine 55. J. Like that. And then now notice again, it's positive in the x direction and positive in y direction. So these are both positive. So when you put this in your calculator, I got the 12.62 I plus 1802 J. And so if we want to find the velocity of A with respect to B, then remember we have to use this equation, which is on your equation sheet. Again, I picked the one that has velocity of A with respect to B. And always remember, it's actually pretty easy to remember that if you want the A with respect to B here, you have to start on the left-hand side. It's going to be VA. So it'll always be VA, and then it'll be A on top over here, and then B will be in the middle. If it was the velocity of B with respect to A, you have VB over here, then B over A, and then VA in the middle. And now all we have to do is put our values in. So over here, we have this. Let me just move this up just a little bit. So put this in negative 7.61 I plus 16.31 J. I'm just putting VA into here into our equation. Then we're going to need VB. 12.62 I 1802 J plus VAB this, and you can work with either side that you prefer. I'll keep the VAB over here. And then, so we'll put together the I components. And so when we bring this to the other side, that's going to be negative 20.23I. And bring this to the other side, negative 1.71J and VAB. Velocity of A with respect to B is negative 20.23I, minus 1.71J. We want to make it look a little bit nicer. You can write it this way. It always looks a little bit nicer this way. Now that's the vector, and that's the most important part of this problem, is to get this vector. The rest of it is important, but not nearly as important as this. Now, if we want to find the actual magnitude VAB, remember that's going to be calculated this way. Negative 20, or I guess we hadn't. I've usually put just VAB without the vector sign. We'll give the magnitude. So the magnitude minus 20.23 squared plus negative 1.71 squared, and square root gives 20.30 feet per second. So finally, if you want to know the distance, whether you call it S or whatever, remember S is going to be velocity times time. And then, so in this case, we know that we want to know when they're 1,700 feet apart. And we have the velocity here is 20.3 feet per second times t. And if we divide and I got 83.74 seconds. That's when they're going to be that 1,700 feet apart. Let's take a look at this problem. This is a problem from Hibbeler. And this says, at the instant shown, cars A and B travel at 70 and 50 miles per hour respectively. If car B is decreasing its speed at 1,400 miles per hour squared, while A is increasing at 800 miles per hour squared, determine the acceleration of B with respect to A. Now notice that car B moves along a curve, so that's not a straight line that B is moving along. There's a curve. It's not real severe, but it has a radius of 0.7 miles. So let's take a look at this problem. So we have this situation here. A is going this way at 70 miles per hour and accelerating at 800 miles per hour squared. And then B is moving this direction 50 miles per hour and decelerating. So we'll have to put negative for its acceleration. It's decelerating at 1400 miles per hour. So let's take a look at this. And now let's start with the easy one. Let's start with car A. Let me put it over here. So car A, it's easy because it's just moving vertically. So the velocity of A is going to be 0 in the x direction, and it's going to be 70 in the y direction because it's just going north. And acceleration of A, once again, nothing in the x direction, and 800 in the y direction. So now let's take a look at car B, and we might need to make a little bit of a diagram here to kind of get our bearings. This maybe is car B. This, and it's going in this direction. It has, again, velocity B is 50. I'm going to keep the units off so I don't clutter this too much. Acceleration of B is negative 1400. And now, because it's going around this curve, there's going to be a normal acceleration. And that normal acceleration is going to go in this direction. And we're told that this is 30 degrees. If you look at the original problem, that's 30 degrees. And that means this is going to be 60 degrees. This normal coming down, like I said, there's going to be a normal acceleration here. And so this is going to be a right angle. So this is also going to be 30 degrees. So now let's see if we can put this together. Now the normal acceleration, you recall, is always going to be velocity squared over rho. In this case here, our velocity is 50. Our rho, the radius of curvature, is 0.7. Maybe this should be square here. And when you put that in your calculator, you get 3571.4 miles per hour squared, like that. Then we'll find the acceleration. It looks like it's not asking for the velocity, so we can just work on the acceleration right now. So let's break this down. So now we're going to have to make an acceleration vector for car B. And notice that we have to consider a couple of things. We have to consider this tangential acceleration and this normal acceleration. So we're gonna have to break each of those down into components of x and y. And so let's do that here. So we're going acceleration of b, we're going to make the vector, and it's going to have an I component, of course, and a j component. And I'm leaving myself a lot of room here because, as I mentioned, we have to consider the tangential acceleration and the normal. First of all, let's look at the tangential acceleration. It's minus 1400. And then the x component will be the adjacent to this. So it'll be minus 1400 cosine 60. Like that. And then let me go over here for the, again, we'll work with a tangential. For the y component, it would be minus 1400 sine 60. Like that. So I just took, you remember, the adjacent's always a cosine, so we have 1400 minus 1400 cos 60. And for the y component, we have minus 1400 sine 60. Now let's look at this normal acceleration. So again, the x direction, notice it is going in the positive x direction. So once again, we use the adjacent here for the x component. So that'll be 35, 71.4 cos 30. And now notice for the y components going downwards, so that's going to be negative. So that'll be negative 3571.4, and this will be sine 30. So let's calculate those. And when I put that in my calculator, I got, when I did this over here and added those together, I got 2392.9 I. And then when I did those over here, I got negative 2998.1 J. And these are miles per hour squared. Like that. And so we're asked to find the acceleration of B relative to A. So let's do that next. And so the acceleration, and remember, to do that, we have to use this equation. Remember, if we need B relative to A, we have to set up the one that says A acceleration of B, excuse me, acceleration of B equals acceleration of A plus acceleration of B with respect to A. And so now let's put everything into our equation. We just found acceleration of B. So let's put that in here. 298.1 J. And equal to acceleration of A. Remember, we found the acceleration of car A up here. It was 0I plus 800 J. And then our unknown is acceleration of B with respect to A. And then let's solve for this. So this is 0, so it's not going to be anything. And then let's bring this to the other side. So this is going to be, I is not going to be affected. And then we're going to subtract this, the 800 over here, minus 3798.1 J. So that's the acceleration of B with respect to A. If you want to make it look a little bit nicer, you can write it this way. Like that. And if we want the magnitude of this, we can just take the magnitude of that, and that's going to be the square root of the sum of the squares. And put that in your calculator. That's 4489 miles per hour squared would be the magnitude. This is also, of course, miles per hour squared.